All right, I think I can take one more video before going home. This is going to be the second video of the third week. So in this video, let me use the new lecture slide I just posted on the course website. So now the first topic is relationship between Pareto optimality and the social optimal allocation. All right, so the first topic is, so we are going to study two topics in these new lecture slides. The first one is we get into Pareto efficiency. All right, so we studied the notion of Pareto efficiency. I think you've studied that in intermediate microeconomics class. So there is no other way to make one agent better off without the some other agents worse off, right? And so we are going to relate this notion to social welfare maximization problem. Okay. To better understand the notion of Pareto efficiency. Okay. So we are going to link Pareto efficiency and the social welfare maximization problem after introducing the social welfare function. And moreover, we derive conditions which characterize the efficient allocation under some assumptions on utility function and production function be differentiable. Okay, and the second topic is a positive theory of Wallergen equilibrium. Okay, so we are going to test on the predictive power of Wallergen equilibrium. Okay, so in this short video, let me cover just one topic, so introducing social welfare function and the relation between Pareto efficiency and social welfare maximization problem. So the motivation is this. We studied two welfare theorems, and the welfare theorems tell us economy will be Pareto efficient when the economy is perfectly competitive, meaning that the uh, agents' behavior are price taking, so nobody has a power to control the price. So the price is only determined through competition in the market. And the economy is an equilibrium, meaning that all agents now achieve some maximization, right? For consumers, utility maximization, and for firms, Pareto efficient, the profit maximization, right? So the all agents achieve their own objective given some constraint. For consumers, budget constraint, and for firms, some technology constraint. Right? So there is some nice mapping, nice correspondence between market mechanism, so what market can achieve, and efficient allocation. Okay, so that correspondence is captured by the two welfare theorems. Okay, the intuition is quite simple. So if a unit of goods and services could have produced more, okay, so or could have brought some more satisfaction, so higher utility for some consumer, you know, other than its present use, then some firms or consumers would have been willing to bid up its price because they want more, right? Because they have some firms can produce more with the resource, other than firms, and consumers can enjoy higher utility by consuming that good, compared to the current situation. Then they would demand more, right? That increases the price, right? So they will bid up higher price and is willing to take that good or service in a market mechanism. So in a market mechanism, that is possible. So that kind of, some economic force would change the demand and supply. That is not an equilibrium anymore, right? So in a state of equilibrium at least, this kind of thing, so the improvement of efficiency cannot happen, right? And the one natural question that arises in this context is, so we know market equilibrium achieves efficiency, and any efficient allocation can be achieved by market mechanism under some strong assumptions. And the next question is, what is Pareto efficient allocation? Right? So is a Pareto efficient allocation from the social point of view is the most desirable outcome, right? If that is true, then we can say market achieves the most desirable outcome, right? But we, from the two welfare theorems, what we can tell is just a market achieves Pareto efficiency. Okay, so we have to better understand this Pareto efficiency by getting into this notion. So then, in order to answer this question, we have to think about what is a socially desirable outcome. All right, and there are much philosophy, about this. So I'm not going to get into this. And so we examine this question from a utilitarian perspective, founded by, greatest philosophers like Jeremy Bentham and John Stuart Mill. Utilitarianism, the main slogan is the greatest happiness for greatest number of people. So in Korean, 최대 다수의 최대 행복이요. So from a utilitarian perspective, socially desirable allocation is the allocation that maximizes utility or well-being for all individuals. Okay, so from this perspective, so by taking utilitarian perspective, we are going to examine the question, Pareto efficient allocation is a socially desirable outcome. Okay, and then the answer is yes. Right? So in order to address this question, we begin with UPS, utility possibility set. So this set is a counterpart of production possibility set in producer theory. So the set indicates the set of attainable vector of utility levels given resources, available resources in the economy. All right, so the formal definition is right here. This is the set, so set of utility levels for consumer for consumer I to level for consumer one, for the level for consumer one to the level for consumer I. So this level is attainable, meaning that there exists a feasible allocation x and y such that if a allocation of a good across consumer, so the goods are distributed according to x, then each consumer can achieve at least ui of xi, and this specified utility level u super I is lower than this, so u super I is attainable. All right, so here is the picture of a possible UPS. Then suppose we just choose one point here. Okay, that is in the set, meaning that this utility level. So for consumer one, this level of utility, and for consumer two, this level of utility is attainable in the sense that given the available resource. Given the available resource in this economy, there is a way to achieve this utility, so make this utility for these two consumers. Okay, so this is attainable, so we can make a consumer one worse off. Making worse off is easy, but making better off is difficult, right? So from at the fixed level of utility level for consumer two, we can make a consumer one worse off, or at the fixed level of utility level for consumer one, we can make consumer two be worse off. Right? So the utility set, the UPS can take this kind of shape. So it goes a negative infinity, or negative infinity for consumer one and negative infinity for consumer two. And it has a boundary like this. And this boundary, actually not whole boundary, but it's a portion, is called a frontier. So utility possibility frontier. But it does not include this one. Okay? It's just a so utility possibility frontier indicates the northeast region, so northeast boundary, in the sense that so frontier is the set of utility level such that there is no other utility level obtainable given the resource, given the available resource in this economy, such that some consumer I enjoys a higher level at this allocation V than allocation U, and so for all I, okay, for every consumer I, so for every consumer I prefers, so enjoys a higher utility at allocation V than allocation U, and VI is a strictly higher than UI for some consumer I, for some I. Okay. So it is linked to a Pareto efficiency. Right? So here, here at U hat, so at this utility level, at this utility vector, if you want to increase the consumer one's utility, it is impossible. So while maintaining consumer two's utility, so in order to increase consumer utility, consumer one's utility, we couldn't. So we have to decrease consumer two's utility. So it goes this direction, right? So the southern-eastern direction. Right? So if we increase consumer one's utility, without hurting consumer two's utility, then we will be outside of this UPS. Okay, so that is a frontier. But here, in this region, we can increase consumer one's utility without hurting consumer two's, right? So this is not a frontier. The frontier indicates that just the northeastern region, the northeastern boundary of the whole boundary of UPS. Right, so Pareto efficient allocation must be in the set U, because by definition of efficiency, there must be, so it must be feasible allocation. Right, so it must be in the set U. More precisely, Pareto efficient allocation is one portion of the boundary of the set U that is a northeastern frontier, like this. Okay. And just one more thing about this UPS. So it does not have to be convex always, but under some conditions, under convexity assumptions. So whenever all consumers' preference relations are strictly convex and production set is convex for all from J, then we can show that the set of attainable vectors of utility is a convex set. So it looks like this. So whenever we have 2 points inside the set, so this utility level is attainable, and this is also attainable, then any linear combination between these 2 points, so any utility levels on this line segment are also attainable. Okay. So I leave this for exercise, but this exercise is not that straightforward. The proof is a little bit intricate, but it is in the exercise. It is in the list of exercises in chapter 16 in Musgrave Instant Green. So if you have a difficulty, then you may refer to the solution manual. If you have a difficulty even with the solution manual, then you can. You may contact me, then I can discuss with you. All right, and then so that is a UPS, and then now let me introduce social welfare function. Social welfare function is a function of individual utilities, but we are going to consider the simplest social welfare function that is given by a linear function, linear combination. So here U super I, consumer one's utility level, U super U super 1, consumer 1's utility, U super I, consumer I's, the last consumer's level of utility, and then we assign some weight on each consumer's utility. Okay? And then take the linear combination and define social welfare function as this linear combination. So using summation notation, we can write this way, or using the dot product. So vector U, or the letter U, is a collection of level of utilities for all consumers, and vector I is this weight U super I. So U super 1 to U super I. Okay. Then using these two vectors, we can write this as dot product between U and lambda. Okay. So the linear social welfare function is a weighted sum of individual utilities. So whenever this weight lambda, so lambda should be non-negative number, because if lambda was a negative, it means if some consumer is better off, so his utility increases. On the other hand, social welfare decreases, right? So it contradicts with a utilitarianism. So now we are taking utilitarian perspective, meaning that all weights are some positive, some non-negative numbers. Okay. If we assume equal weight for all consumers, then that exactly corresponds to utilitarianism. All right. So with this social welfare function, this lambda is called a welfare weight or Pareto weight. So this vector weight vector lambda is called a Pareto weight vector or welfare weight vector. So if lambda super 1 is a large number, it means from social welfare point of view, the consumer one's welfare is quite important, right? So for the society, concerns about the some economically unstable people, like poor people, then this is a welfare for the poor people with a low income. That might be the highest. That might be an of a highest importance. Then lambda 1 is going to be a very large number, right? And the this kind of interpretation can be applied. All right, and then so given a weight vector lambda, now we consider welfare maximization problem. So lambda is given. Okay, some society may concerns most for a poor people, or some society may concern about the utilitarianism. So they may concern about the all individuals' utility equally. Does not matter. Given weight vector lambda, we consider welfare maximization problem. So the problem can be written as, because the utility level should be attainable. Oh, by the way, I forgot the important assumption here. So when we analyze the this kind of problem, social welfare problem, we make an important assumption, that is, utility can be quantified. Okay, so the number of utility now matters. It has some meaning. So utility 10 is different, from utility 20. So when you study intermediate microeconomics, you may learn cardinal utility or ordinal utility, right? But when we study consumer theory itself, we work with ordinal utility function. So any monotone transformation of utility function still represents the same consumer's utility. That is ordinality, right? But for social welfare function analysis, we take a cardinal utility concept. So utility number 10 now is different from utility number 20. Okay. All right. So yeah, I guess you guys have a solid understanding about cardinality and ordinality. But if you have some difficulty, just contact me. All right. In fact, I held a some Q&A session this Wednesday. So yesterday at 3 p.m. But I couldn't see anyone. I mean, I stayed in the gym for 15 minutes, so until 3:15, and nobody attended the session. So it's a little bit hard to interpret that because it means nobody has a question or nobody understands this course material. But anyhow, if you have some difficulty, don't hesitate to come by my office or contact me. And we can individually meet or we can talk in a virtual space using the software Zoom. All right. So under the assumption welfare or utility is quantifiable, so now we consider welfare maximization problem, and so U star. So here, welfare maximization problem is now we maximize social welfare W, right? This function W, given the constraint that this utility level should be attainable given the available resources. And then U star denotes the solution to this problem. Okay, so the maximizing social welfare function. And since U star should be in the set UPS, right? So that is attainable, meaning that there exists a feasible allocation X star and Y star, and this U star should be lower than and equal to this utility level, right? Otherwise, if inequality was reversed like this, strict inequality, then if there's a no feasible allocation that attains U star, so that contradicts with the assumption UPS. So we must have this inequality. And then we call this, okay, so the feasible allocation that enables us to achieve the utility level U star, the socially optimal allocation given weight vector lambda. Okay, once again, the welfare maximization problem would be different. That depends on lambda. Okay, so different lambdas will give us different solution U star. So this U star, you can easily anticipate this U star depends on weight vector lambda. Okay. So given weight vector lambda, we find a solution U star, and then we can find a feasible allocation that enables us to achieve this utility level. Then we call this allocation X star and Y star the socially optimal allocation. All right, and then so I think I can finish. This is gonna be the last slide of this video because I should go home. So now the next result shows the relationship between a Pareto efficient allocation and socially optimal allocation. Okay, so this is a proposition 2.1. So if U star solves the problem number 1, so that means U star is a socially desirable in the sense that it maximizes social welfare function, then U star is on the frontier in the set UP frontier, right? That means U star is a Pareto efficient. So social welfare maximization means Pareto efficiency. That is the first statement. Okay, and then this statement is straightforward because suppose that U star serves so U star maximizes social welfare function. And by the way, here lambda is a strictly positive. So here lambda is a vector. So lambda 1, from lambda 1 to lambda I, and that is larger than 0, and this 0 is also a vector. So all weight is a strictly positive. Each weight is strictly positive. So with a strictly positive weight vector, suppose that U star serves a problem, the social maximization problem, but is not Pareto efficient. So it's not on the frontier. It is, it is a right here. not on the frontier, but inside the set. Then, we can easily increase a social welfare function because there is some room to the boundary, to the frontier. And if we move this direction, then we can increase the social welfare function. So, if U star maximizes social welfare given this positive vector, then it should be on the frontier. This statement is very straightforward. There's nothing to prove. But the second statement is a non-trivial. So it states that if the set U, so UPS, is convex, it looks like this. Okay? And then for any U star on the frontier, so like this one, like this U star, okay, this U star is on the frontier on the northern-east boundary, then there exists a vector lambda such that lambda dot U star, so that is a social welfare, okay, given lambda, is higher than any lambda than U for all attainable U in the UPS. So in other words, there is some line segment or hyperplane, okay, hyperplane. So this UPS, the entire set UPS, so all attainable utility vectors now below this hyperplane. So the second statement states that the second part of this proposition 2.1 states that if U is convex, okay, then there exists this kind of hyperplane line segment in two-dimensional space, such that we can lie the UPS, the whole obtainable vectors of utility below this hyperplane. All right. So in other words, social welfare. Now that is a mathematical explanation of this second part. Now economic interpretation is, so if U is convex, then U star is on the frontier. So U star is a parity efficient allocation. Then lambda dot U star, that is a social welfare at that parity efficient allocation. Okay, so this actually maximizes the social welfare function. So that is the converse of the first statement. The first statement is social welfare maximization means parity efficiency, and the second part is parity efficiency implies social welfare maximization, but for some specific lambda. Okay, so the second part implies that every parity efficient allocation can be viewed as a socially optimal allocation for some weight lambda, not all lambdas, not always, but for some lambda, specific lambda weight. Okay, and this part is immediate from separating hyperplane theorem. So if you study the Kuhn-Tucker theorem, into depth, like by taking mathematical economics or some advanced math for economists, you may heard of this theorem. So that theorem has two versions. Whenever we have convex set disjoint like this, set A and set B, and this theorem states there is some hyperplane, perfectly separates A and B. So let me call this hyperplane lambda. Then lambda dot A is larger than lambda dot B for every entry A in set A and small b in the set B. Okay, so there exists such a lambda such that there exists a lambda, hyperplane lambda, such that dot product with any element in the set A is always higher than dot product with the element in the set B. That is the first version. The second version is this. So using this one, okay, so we have a convex set, closed convex set, okay, closed convex set. Then, there exists a hyperplane such that, so the second version can be described this, okay. So we have a one set here, and the other convex set here. Okay, now they share some points. Okay, so not perfectly disjoint, right? But they share only boundary. In other words, they do not have common interior points like this. Okay, then they have some common interior points, between these two sets, but they share some points. They have some common points, but only on the boundary. Then still, if these two sets are convex set, then we have a separating hyperplane. But for this case, unlike these two cases, now inequality is a weak inequality. We have this, separating hyperplane theorem. So this part, the second part of proposition 2.1 is immediate from separating hyperplane theorem because U is convex, and then we have one point on the boundary. Then there exists a hyperplane that separates this and U and the other convex set, like this one, okay. So this hyperplane, locates the UPS below this one. So in the sense that perfectly separates UPS with the other set. Okay? So there exists another convex set above this hyperplane and below this hyperplane. So the hyperplane perfectly separates these two sets. All right. So I'm not going to prove this statement formally. If you wonder, you may refer to our textbook, but that proof is not that intuitive. Not economically intuitive. It's just a mathematical statement. But at least this proposition, implication of this proposition is important because it establishes some close relationship between Pareto efficiency and social optimality. All right. So going back to our first question, is a Pareto efficient allocation socially desirable outcome? So socially desirable outcome is always Pareto efficient. But if we are asked, Pareto efficient allocation is always socially desirable, then for some weight lambda, then we can say yes, right? But not for every lambda, that the answer is no. All right, so we can establish such a some not perfect, but as some imperfect relation between efficiency, Pareto efficiency, and social optimality. So this is the end of the second video. It's still 32 minutes, all right? And in the next video, we are going into Pareto efficiency a little bit more by deriving conditions under which by deriving conditions that characterize Pareto efficiency. All right. I think I can take this video tomorrow, Friday afternoon, and then see you in the next one.